You've probably heard the term greenhouse effect a million times, right? It usually pops up when we're talking about climate change, and honestly, it almost never sounds like a good thing. But is it really the bad guy in this story? Or is there more to it? Well, let's get into it, because the truth is, it's a little more complicated than that.
Okay, so first things first. Before we dive into all the heavy stuff, let's be super clear about one thing. The natural greenhouse effect isn't the villain, not at all. In fact, without it, none of us would even be here. It's kind of like Earth's own invisible, perfectly tailored blanket.
And to really get a sense of just how important this blanket is, let's try a little thought experiment. What if we could just poof, snap our fingers and make that entire atmosphere, that entire heat-trapping layer, just disappear? What would our world actually feel like?
Yeah, that's the answer. Our planet's average temperature would drop to a staggering minus 18 degrees Celsius. For those of you in the US, that's around 0 Fahrenheit. We're not just talking chilly here. We're talking about a completely frozen, totally uninhabitable ball of ice. Suddenly that blanket sounds pretty essential, doesn't it?
So this is the key number to remember. This whole natural process gives us a 33 degrees Celsius boost in temperature. That's a whopping 59-degree jump in Fahrenheit. It's what takes us from that frozen wasteland scenario to a pretty comfortable global average of 15 degrees Celsius. It is, and this is not an exaggeration, the difference between a dead planet and our living, breathing world.
Okay, so we've established it's a good thing and a necessary thing. But how does this planetary heating system actually work? Let's peel back the layers and look at the mechanics of how this global blanket does what it does.
At its core, the definition is actually pretty simple. Certain gases in our atmosphere basically act like a one-way mirror for heat. They let sunlight in, but they don't let all the heat back out. It's a simple idea, but with incredibly powerful consequences.
So let's break this down. First, the sun's energy, which is high-energy short-wave radiation, just zips right through the atmosphere and warms up the ground. Easy enough. Then, the Earth sends that energy back out, but this time it's as lower-energy heat, what we call long-wave radiation. And now, here is the absolute key. Greenhouse gases are uniquely good at grabbing that specific kind of long-wave energy, trapping that heat before it can escape into the cold of space.
And here's something that might surprise you. The name greenhouse effect is actually kind of misleading. A real greenhouse, the glass building, works by physically stopping warm air from rising and blowing away. But that's not what's happening on a planetary scale. The atmosphere doesn't physically trap air. It absorbs energy. That's why a blanket is a way better analogy. A blanket doesn't make its own heat, right? It just slows down the rate at which your body loses heat. That's exactly what these gases do for the Earth.
Now, I want you to look at these dates, because this is not some new idea. The basic science is almost 200 years old. We had Joseph Fourier suggesting this back in the 1820s. Then, a pioneering scientist named Eunice Newton Foote actually proved it in a lab with CO2 and water vapor in 1856. By 1896, Svante Arrhenius was already calculating how much the planet could warm up if CO2 levels doubled. This stuff is foundational science.
And just take a moment to appreciate this quote from Eunice Foote's paper from 1856. An atmosphere of that gas would give to our Earth a high temperature. It's just an absolutely incredible piece of scientific foresight. She understood the fundamental connection more than 160 years ago.
So, if the natural greenhouse effect is so vital, so necessary for life, where did things go wrong? Well, this is the big plot twist in our story. We've gone from having this perfect, cozy blanket to suddenly piling on way too many extra layers.
And that brings us to what scientists now call the enhanced greenhouse effect. It's the exact same process we've been talking about, the same physics, but now it's being put on steroids, supercharged by all the extra greenhouse gases we humans have been pumping into the air.
Let's look at the numbers, because they really tell the story. For hundreds of thousands of years, right up until the Industrial Revolution kicked off, the amount of CO2 in the atmosphere was pretty stable. It hovered right around 270 parts per million. You can think of that as Earth's natural setting.
Fast forward to 1960, that number had already jumped up to 313 parts per million. That's not a small change. It was a clear sign that the actual chemical makeup of our atmosphere was shifting. And today, we've soared past 400 parts per million, and it's still climbing. We are now at levels that are far higher than anything our planet has seen in at least the last 800,000 years. The bottom line is simple. Our planetary blanket is getting thicker, and it's happening incredibly fast. And there's really no mystery about where this is coming from. The main engine is the burning of fossil fuels. For our cars, our power plants, our industries. But it's not just that. It's also how we use land. Things like cutting down forests and large-scale farming also release an enormous amounts of these heat-trapping gases.
You know, to really see how powerful the greenhouse effect can be, we don't have to look at computer models. We can just look up. A quick tour of our planetary neighbors gives us some pretty stunning, real-world examples of this principle in action.
This chart tells such a cool story. First, look at Venus. Its atmosphere is almost all CO2 and super thick. The result? A mind-blowing 503-degree warming effect. Now check out Mars. It also has a CO2 atmosphere, but it's incredibly thin, so it only gets a tiny 6-degree warming bump. And then there's us, Earth, sitting right in that sweet spot, that Goldilocks zone, with just the right atmospheric mix to give us our life-sustaining 33-degree boost.
So you can really think of it like this. Venus is the ultimate cautionary tale, a runaway greenhouse effect so intense that it's actually hotter than Mercury, even though Mercury is way closer to the sun. Mars shows us what happens when your blanket is too thin. And Earth? Well, for a very long time, Earth had the balance just right. And this is the part that's so important. The very same laws of physics, the same science that lets us predict the oven-like temperatures on Venus and the deep freeze on Mars, is the exact same science that tells us that adding more heat-trapping gas to our own atmosphere is going to make our planet warmer. It's not a different set of rules. It's a universal principle.
Which brings us right back here, to the one question that really matters. We have seen how a planet's atmosphere can literally define its destiny, turning one world into a furnace and another into a freezer. We know for a fact that our own essential life-giving blanket is getting thicker every single year. The science is clear, so the only real question left is, what happens next?